Study with Artemis, Inc. podcast. This information was produced with the assistance of AI content. Introduction to sound waves. This audio presents an examination of sound waves, a fundamental concept in physics integral to our daily experience. Sound, a form of energy, propagates through a medium as waves. Unlike electromagnetic waves, which can traverse a vacuum, sound waves necessitate a medium, such as air, water, or solid materials, for transmission. These are mechanical waves, characterized by the transfer of energy through the vibration of particles within the transmitting medium. The nature of sound. Longitudinal waves. The propagation of sound involves specific vibrational patterns. Sound waves are classified as longitudinal waves, a type of mechanical wave wherein particles of the medium oscillate parallel to the direction of wave propagation. This mechanism can be visualized by considering a slinky subjected to a push and pull at one end, resulting in compressions and expansions along its length. Similarly, a vibrating speaker cone generates regions of elevated pressure, compressions, and reduced pressure, rarefactions, in the adjacent air. These pressure variations propagate outward from the source, thereby transmitting sound energy. Key properties of sound waves: wavelength, frequency, amplitude, and speed. Several key properties define the characteristics of a sound wave. Wavelength, lambda. This metric represents the spatial period of the wave, specifically the distance between two successive compressions or rarefactions. Frequency, f, defined as the number of complete oscillations, cycles of compression and rarefaction, passing a fixed point per unit of time. Frequency is measured in Hz Hz, where 1 Hz corresponds to 1 cycle per second. Frequency directly correlates with perceived pitch. Higher frequencies result in higher pitches, and lower frequencies in lower pitches. The typical human auditory range spans approximately 20 Hz to 20,000 Hz. Amplitude. Amplitude quantifies the maximum displacement or pressure variation from the equilibrium position of the medium's particles. It is directly proportional to the loudness or intensity of the sound, with greater amplitude indicating a louder sound due to increased energy transfer. Amplitude is commonly measured in decibels, dB. Speed, v. The speed of sound refers to the rate at which the wave travels through a medium. This speed is contingent upon the medium's intrinsic properties, primarily its elasticity and density. Sound propagates more rapidly in denser and more elastic materials. For instance, sound travels significantly faster in steel than in air, and faster in water than in air. Under standard atmospheric pressure and at 20 degrees Celsius, the speed of sound in air is approximately 343 meters per second, m/s. These four properties are interrelated by the fundamental wave equation. V equals F lambda. Behavior of sound waves: reflection, refraction, diffraction, and interference. Sound waves exhibit distinct behaviors upon interaction with their environment. Reflection. This phenomenon occurs when a sound wave encounters a barrier and is redirected back from the surface. Echoes exemplify sound reflection. The efficacy of reflection is influenced by the surface characteristics. Hard, smooth surfaces are highly reflective, whereas soft, irregular surfaces tend to absorb sound. This principle is fundamental to acoustic design in spaces such as concert halls and recording studios. Refraction. Refraction describes the change in direction of a sound wave as it transitions from one medium to another, or as it traverses a medium with varying properties, e.g., temperature or density. This alteration in the medium's characteristics causes a change in the wave's speed and, consequently, its direction. An example includes sound waves refracting when passing through atmospheric layers of differing temperatures, leading to the bending of sound over water or open terrain. Diffraction. Diffraction involves the bending of sound waves around obstacles or through apertures. This explains why sound can be heard from around a corner even if the source is not visually accessible. The extent of diffraction is dependent on the wavelength of the sound relative to the dimensions of the obstacle or opening. Longer wavelengths, lower frequencies, exhibit greater diffraction than shorter wavelengths, higher frequencies. Interference. This phenomenon arises when two or more sound waves superimpose. The superposition can result in either constructive interference, where amplitudes combine to produce a louder sound, or destructive interference, where amplitudes cancel, leading to a quieter sound or even silence. Noise-canceling technologies, such as headphones, leverage destructive interference to mitigate ambient noise. Conclusion. A comprehensive understanding of the properties and behavior of sound waves is crucial not only for physicists but for anyone seeking insight into auditory perception, from musical acoustics to communication, and in technological applications such as sonar and medical imaging. Sound represents a potent and complex form of energy, continually shaping our auditory environment. Copyright 2025. References: Hall, D. E. 2005. Musical Acoustics. Thomson Brooks / Cole. Cutnell, J. D. and Johnson, K. W. 2012. Physics, 9th edition. John Wiley & Sons. Young, H. D. and Friedman, R. A. 2012. University Physics with Modern Physics, 13th edition. Pearson,